All right. So today we'll do some examples. Application of dimensional analysis. All right. Okay. And examples. Okay. So up to now, we had some dimensionless groups here. All right, which is the output is equal to some function of some dimensionless groups here. Okay. All right. This dimension. Don't worry. I put not now. Later I'll put something in that inside there. Okay. And remember I told you that if this for a particular problem, if these parameters are the same, okay, then you expect the same output. All right. That's the theory anyway. Okay. So today, the two things we'll do. We'll do problems where it's maybe a unique problem. Okay. So you don't know what it is in the full scale. All right. So instead of building the bridge first, you build a model and test it. All right. Bridge is complex problem, so there's no standard one. And number one. Number two is if there are standard problems, like flow past a cylinder or something like that, then most likely someone already done it. They plot the graph. All right. And then we just apply that graph. So there's two applications here. All right. That's why I brought my textbook also, all the graphs in there. Okay. So number one, let's say it's some weird problem you have. Okay, weird lah, unique problem you have. Okay, so maybe this one pipe diameter D. Okay, got full scale. Maybe in full scale you have some air going through here. All right. And you have some spiral in here. Okay, some helix spiral. This one has a diameter small d. Okay, some wire. All right. And okay, normally this type of inserts you have inside the pipe is try to enhance the mixing in the pipe or enhance heat transfer or something. Okay, do some mixing. So the pipe, so the flow is not just going straight in the pipe. At least there's something to mix it up a little bit. Okay, for example, all right. So normally they call inserts or mixers or whatever. So this one is static, and the input parameter that we can control. Okay, we can control D. We can control small d. Big D is the diameter of pipe. Small d the diameter of the wire. We can control some angle theta. This is the helix angle. We can control the number of turns n. All right. Okay, n being the number of coils. All right, we can control. We can control the velocity of the air and the properties of the liquid. All right. Anything else you think the problem dependent on? Huh? No lah. This one no gravity lah. Okay. This problem not normally no gravity. I told you mainly the free surface type problems. Right, where there's a gravity is a restoring force. Here's pipe full of liquid. Whether most likely moving horizontally, gravity doesn't matter. So I can't think of any more. So let's leave it as that. Okay. What's the output parameter you worry about? Maybe what we worry about? Okay. Maybe some sort of mixing parameter, but since we don't know any measure of mixing, never mind. Let's say. What is it? Okay. Maybe we are concerned about a vibration problem. Okay, the flow will go around this one and it cause the turbulence and all that and cause some vibration. So we worried about the frequency, say. Alright? We make sure the frequency of the flow, of the excited flow, does not match any frequency of the structure that's holding the pipe or anything like that, after the pipe break. Okay, or the structure break. Alright? So this one don't call F lah. Call maybe G. F, G. Alright, some function doesn't matter. Call phi. Okay? So Normally, if you look like this, our usual suspect is rho V D as the repeating variable. Okay? I'm going fast now, because I already done it. I already know. Okay? So F, alright, if you do the thing that we did the last time, you will get F L over V. Correct or not? That's your Strouhal number. Alright? It's a function of small d over big D is one parameter. Theta and rho V D over mu. And anything else? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we expect 5 terms, correct. Alright, we started off with 1, 2, 3, 4, 5, 6, 7, 8. 8 parameters. We have 3 dimensions, alright. M, L, and T. So we expect 5 groups. Okay, 1, 2, 3, 4, 5. I did very fast, Let me explain. Okay, so small d over big D is a dimensionless group. No need to, you can prove for yourself if you want. Alright, you can do the small d over rho to the A, D to the B, D to the C equals to dimensionless, dot 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 dot, and somehow you should get here. Okay, that's your homework. For those who don't believe, theta, what's the dimensions of theta? Dimensionless. So if the dimensionless already, there's no need to dimensionless it anymore. It is dimensionless. Okay? You can try also. If you don't believe, you can put theta over rho to the A, B to the B, D to the C. You'll find A equals to 0, B equals to 0, C equals to 0. Okay? You don't believe, you do. Alright? You believe, then it's pretty straightforward. Dimensionless is okay. Radians is no dimensions. It's length over length, so it's dimensionless. And number of coils, what's the dimension? Dimensionless. So n already there. Okay. And then the mu. Well, we've done that many times, Alright. Mu dimension group together rho v and d. You'll get the Reynolds number. So this is the Strouhal number, and this is the Reynolds number. The rest are just a length ratio, theta n. Okay? So example, e.g. Alright? We do this one very big. Okay? Maybe lah. Let's say very big in air. Alright? We don't have the test facility to build a big one in air. So we do in water. Okay? So we test in water. Test in water. Okay, so the actual one, the prototype or full scale, PRO, prototype. Okay, prototype is what? Okay, the velocity maybe 5 meters per second, maybe too high, 3 meters per second in air. Okay, so maybe the theta is equal to 30 degrees. Alright, or how many radians doesn't matter. Okay, 30 degrees equals to 30 over 180 times pi. Is that right? I think so. Okay, radians. Alright, and maybe 5 coils. Okay, d theta n. Anything else? Okay. And big D is maybe 1 meter. Small d is maybe 0.05 meter. Something like that. Okay? So this is the prototype dimensions that you want to design. Okay? Right. But we are going to test in water. Okay? So our water, our small d, big D maybe uh, 0.2 meters. Okay, maybe that's our dimension of our pipe. Okay, so what should our small b be? All right, so remember, the input parameters must be the same so that the output is the same. Wow. Okay, so small d, we do the easy one lah. This is basically just geometry scaling. Okay, big D over small d of the model. So this is the model lah. Okay, the testing model. All right, of the model is equal to small d of big D of the prototype. Is that okay? So the length rate. So look, it is geometrically scaled up. All right. So small. In this case, the model is big D is 0.2, small d we don't know. Model equals to small d over here is 0.05 over 1. So therefore, d model equals to, what is 0.2 times 0.05 divided by 1? Huh? 0.01. Okay, meter. Is that alright or not? Okay, so we have scaled it proportionally. Okay or not? Is that alright? Any questions? Okay. So first we need to make sure all our input parameters are the same. Okay. So if you want to test, I make sure the small d over big D is the same now. Okay. Given that big D is 0.2, that's my pipe diameter. I need to go out there and look for a wire diameter that is 0.01. Okay. Search high and low until I get my wire diameter 0.01. Order from UK or whatever, so whichever I have to do. Okay. Either or custom made. Okay. There are some fellas that will roll the wire for you to whatever diameter you want. It costs money, right? Okay. But assuming money not issue here, somebody will. If it's non-standard size, somebody has to roll it out that size. Okay. Any questions? All right, huh? That's the easy part. Okay. Now, if theta here is 30 degrees, what's the value of theta here? Same. Okay, who say not same? Okay, 30 over 180 times pi. Alright. If you haven't figured out what we're doing here, we are matching all the input parameters, the dimensionless input parameters in both prototype and model. Alright. Therefore, and then we conduct the experiment, measure the value, and then we can then predict what the measure the output from the model, and then use that to predict the prototype. That's what we're doing. Okay, that's why n same. N here n5. How many calls here you expect? 5. Okay, obvious, huh? Okay, so this n and this n same. And finally, different. So the more complicated one, we need to match Reynolds number. Okay, so rho VD over mu for the model is equal to rho VD over mu of the prototype. Okay, from here we cannot control rho and mu because that's the property of air and water. Diameter already set, so we can only adjust the velocity of the model to match that of the prototype. I show you here. What is the rho of water? Around 998. Okay. Velocity we don't know. We want to find from this analysis. Diameter is 0.2. What is mu of water? If you don't know, don't panic. Don't need to memorize your formula sheet here. Okay. I believe you should see something very, if not the same one, something very similar in your exam. Okay, so don't need to memorize. You want, you can. So mu of water is 1.2 by 10 to minus 3 Newton second per meter square. Alright, so that's SI unit idea. So 1.2 times 10 to minus 3. 1.2 by 10 to the minus 3. Okay? This one is at around 20 something degrees or 25 degrees or something. Alright? Because viscosity of water very dependent on temperature. Alright? You can go, if you increase by 10 degrees, it might drop instead of 1.2, it will be 0.9 or 0.95 or something like that. Okay? But for our analysis, you assume at standard temperatures, so that's about, standard temperature I think is 25 degrees or something like that. Or 23 or something. Okay. Alright. So this one, air density is what? You cannot remember, check here. Alright. Air 1.23 and 1.8 by 10 to the minus 5 for the dynamic viscosity. 1.23, 1.8 times 10 to the minus 5. Is that correct? No, no need this one. 1.8 and 10 minus 5. Correct. Alright. Velocity was given at 3 meters per second. 3, diameter 1. 1. Okay? So from here, to match the Reynolds number, we can find the velocity of the model. And what is that? Someone calculate? Might be quite high, huh? Problem. Alright? Yeah. Are you clear about what I've done? Alright? So, by doing what I've just done, up to here, I set up my model. Okay? I've set up my model so that given that the model big diameter is 0.2 and is tested in water, I can set up all the other parameters so that all the input parameters are matching. Okay? Okay, what's the model? What's the velocity? 1.23 meters per second. Is that correct? Alright? Okay. Alright, so I would have a dynamically, okay, now this one you have to listen very carefully. I will have a dynamically similar model. Alright? Everything. That's why sometimes the word similitude appears. Alright, I will have exactly a similar, alright, setup in my experiment and the full scale prototype if I match these parameters. Well, that's the theory lah. So far the theory hasn't failed yet. Okay, so all the input parameters are the same. I expect the output parameter the same. Okay or not? So now I conduct my experiment. Okay, conduct experiment. Alright, measure that F in the model is maybe 10 hertz. Okay, example lah. Alright, what is my F prototype? Alright, prototype is question mark. Okay, so if I did my experiment correct, alright, and I set up everything correctly, by right F model FL over V, don't need lah. FL over V model is equal to FL over V prototype. Alright? Does that make sense? So I match everything on the input side. Okay. All this match already. This one match. Measure F in the model and then predict F on the full scale. So if all these are the same, by right, this should be the same between the model and the prototype. Okay or not? Alright? So I measure F on the model to be 10 hertz. So F is 10. Length of the model is 0.2. 0.2 is it? Yeah, it's diameter. So D. Okay, I'm using rho V and D, so D is there. Divided by velocity of the model is what? 1.23. It's equal to F. This one is 1. This one is 3. Alright, so F prototype equals, okay, can you calculate that? 3 times 10 times 0.2 divided by 1.23. What do you get? Huh? What? 1.88? 4.88 hertz. Okay? Hertz is 1 per second, oscillation per second. Okay? Any questions so far? Alright? So that is how you set up. That's how you set up your experiment to match all the parameters, do the measurement on your model, extrapolate to full scale. Okay. Alright, that's the first half of the lecture. The second half, any questions or not? Alright. The second half, a lot of simple problems. Let's see whether you got any simple problem. I think it's here. Don't have. Don't have. Yeah. Okay. All right. Okay. I got a picture here. All right. A lot of simple problems like flow around a cylinder. Okay. All right. We showed the flow visualization, isn't it? We did. Okay. But those who missed out can try this one. All right. Okay. But basically, for simple problem like flow around a cylinder, been studied to death already. Okay. Many people study it and study it very hard. Okay. Look at this way, that way, this permutation, that permutation, and so on. Let's see whether you can look at this video or not. Copy. Paste. Why you not go? Enter. Or download it. Okay, while it's downloading, nearby. Okay, so simple problems like flow past a cylinder, basically studied a lot already. So in this case, you have flow coming in here, U, okay, free stream velocity, diameter of the cylinder, alright, flow properties, rho, mu, anything else? Normally that's about it. Okay, Newtonian flow, alright. So normally the frequency, okay, what happens is in our experiments we saw there's some small roll up here, okay, and there's also the bigger roll up here. Try or not? All right. Normally this one occurs later. All right. Normally we just concern with this bigger one first. Okay. So the two output parameters that we cannot control is the frequency of the shading, all right, and the what else can we control? And say the drag force. What we can control, the input parameters, is rho, v, d, mu. Okay, the fluid properties and the velocity, put v, and the diameter. Alright? Okay, and if I were to do the dimensional analysis, okay, I do shortcut because I've done it already. F L over D, alright, is one of the output parameters. Drag force becomes F drag over half rho V squared D squared. Alright, I think normally. Alright, it's some function of okay, and here rho VD over mu. Okay, very simple problem. So basically, if the rho VD in your problem is the same between two cases, then you expect the same output. Alright? And let's see what maybe I give the video come out. Let's watch the video first so that you can show how it goes. This is a block. Okay? Alright? Well, this one's a square, but similar things happening. You can see this big, so far finished. These big vortices being shaded off alternately. Okay? This one shading off and this one shading off. Right? So it causes a fluctuation and the forces also fluctuate. Okay, now? Not a good video, this one. Alright? This is the big one. The small ones, there could be some smaller ones in here, but it doesn't get captured quite accurately. Right? This one also got video, I think. Right? Okay? This one may be clearer. I don't know what experiment that one. Square cylinder. This one is for round cylinder. Okay? This is captured experimentally using technology called particle imaging velocimetry. It's been around for about, that technology has been around for about over 20 years now. So, you see the flow is captured. I will tell you that one. Okay, there's some magic behind how you get this, but it's captured experimentally. It can also be done through numerical simulations and so forth. Okay, you can see one vortex shading after another. Okay, this happens at low to moderate Reynolds numbers. At higher Reynolds numbers, it will get more chaotic. Okay, this is it's still quite not turbulent yet. Okay, it's still quite quite clean and quite regular. Okay. I think the red and the blue signify vorticity. Vorticity is where the fluid actually it is not irrotational, it's rotating. Okay, so there's a lot of shear. Those red and blue parts, that's where the fluid is at, there's a lot of shear. Because you can see here the boundary between the outside here is where the flow is approximately steady and inviscid, right? Where your Bernoulli equation applies. Inside here, there's a lot of losses, there's a lot of unsteadiness, and your Bernoulli equation does not apply because there's a lot of shear. Alright, from the shearing means you can see there's a big gradient in velocity, isn't it? From fast moving to slow moving. Okay, there's a big gradient in velocity, there's a lot of shear, and there's a lot of losses there. Alright, so irrotational flow, here the flow is rotational or viscous or whatever you want to call it. Okay? No, not necessarily. Higher pressure normally in the front, lower pressure at the back. This red part here is where the flow is shearing. Okay? Flow is shearing, flow is being swirled around. Alright? Where high speed flow and low speed flow are close, the transition part. Okay? So that's shear. Is that okay so far? Alright, so this is the problem. Common problem studied a lot. How to get exit? Okay. Okay. Alright, and show. Okay. Now I can get this on. Alright. So I told you what the parameters were. Okay. Alright. Alright, just now I showed you where the parameters were. This is the problem. Okay. Alright. So if we match this input, we can plot a graph for this one, and it should be the same. No matter who does it and how you do it and so on, as long as you do it correctly, you do it the same way. So instead of every time you want to predict, not likely lah, but maybe, every time you want to predict the shading of a cylinder, shading frequency, or you want to predict the drag force on a cylinder per unit length, okay? Okay? Normally this one, no, sorry, not d squared. Alright, it's normally d times L. That's the frontal area. L is the lap into the page. Okay, that's your A. Alright, anytime you want to predict, you don't need to go do an experiment again. Somebody done already. Alright? In fact, a lot of people have done it. And so far, because this theory is works, okay, all the data more or less collapses onto one line. Okay? That's why you can see different symbols. Those different symbols represent different diameters, maybe done by different people in different labs and all that also can. Okay? So there's two graphs here. Input parameter and Reynolds number. Output parameter, Strouhal number, and drag coefficient. Okay? Drag coefficient, look on this side. Strouhal number, look on this side. Okay? So if I have a, suddenly I'm going around and say, hey, I need a cylinder. Okay? That cylinder, for example, okay? Alright, so copy this one. Copy. Sometimes I cannot paste that directly in here. Oh, can. Okay, so I'm going along. I suddenly encounter cylinder problem. Not quite rare, but sometimes it happens. Okay, and that cylinder, maybe the diameter 3 meters. Okay, velocity 10 meters per second in the wind. Alright, so maybe this could be a chimney stack outside in the wind. Okay, I want to predict at this particular situation, I want to predict the drag force and the shading frequency. That's it. If I predict anything else, this graph cannot tell me anything. Okay, so remember earlier this one. Okay, so I need to match this one. I need to calculate this one, look up the graph, and then I can get these two, and then I can pop the answer back out again. Let me show you how it's done. What is the Reynolds number? So RE for my case. So this is the problem. Okay, RE is okay. Again in air. All right, out air in the wind. RE equals to rho 1.23, V 10 meters per second, D 3 meters over 1.8 by 10 to the minus 5. Is that correct? 1.8 by 10 to the minus 5. Correct. Okay. So what is my Reynolds number? Huh? Alright, about 2 million. Okay? So the other thing to note, this Reynolds number, the range is very big one. It goes from orders of tens to hundreds to millions to 10 million to 100 million. If you were to plot it on a normal linear graph, it's very painful. Alright? You can see the small part all shrink together and the big part all dominating. Okay? So here, to make things look easier, you can plot on log scale. So here, you can see the log scale. And later, a lot of our graphs will be plotted in log scale because the range is just too big. So here it starts at 10. Okay. This is 10. 20, 40, 60, 80, 100. Okay or not? After that, 200, 400, 600, 800, 1000. 1000, 2000, 4000, 6000, 8000, 10,000. Oh yeah, graph run out. Okay? Our problem don't have. After that, yeah, some of you a bit brighter, you can see after that constant. Okay? Well, we can adjust the problem. Alright? FL what? FL over D. It's the same. They put N here. It is actually F. This is actually F. FL over V, sorry. Okay? Sorry, mistake here. V. FL over D won't give you anything. In fact, it's FD over V. Sorry, there's no L here. Alright, sorry. It's FD over V. because that's the density of air. Rho Vd over mu. Right? Rho Vd over mu. Okay? So, okay? Some of you might observe, alright, that's actually constant, and it is quite constant for the, okay? So since it's constant, so let's just use constant. Constant at around 0.21. Okay? Okay, so we expect it to continue. So ST is equal to 0.21. Alright? So, which is equal to F D over V. Alright? Which is equal to F. Our diameter is what? 3. Velocity 10. Alright? So our shading frequency we expect to be, what is it? What's 10 times 0.21 divided by 3? Huh? 0.7 hertz. Alright? That's our, so each, it will complete one full cycle of shading two vortex pair, one from the left, one from the right, every 0.7 seconds. Okay? Every 1 over 0.7 seconds. Huh? Graph of 0.21. Okay, from the graph, okay, you can see here, after a certain Reynolds number, it's not really dependent on Reynolds number anymore. So I extrapolate it out. Okay? Because I didn't have the data here. Okay? Normally, the data for such high Reynolds number is quite limited. Okay. For the drag coefficient, I'm not sure whether constant or not, but our textbook got. Okay. Okay. So if this works, keep the color scheme. Okay, First, I'm supposed to press this button. Then I'm supposed to press this button. Okay? This is page 501 on your textbook. Look at this graph. Alright? There's two. There's a cylinder and a sphere. Okay? Focus. Zoom. Okay, so page 501. Alright? So if you see, there's two graphs here. One is for a sphere and one for a cylinder. We are doing for cylinder now, so we look at the cylinder graph. Okay? So ours is 10 to the 4, 10 to the 5, 10 to the 6, 2 by 10 to the 6. We are around 4 pointer. Right? We are around here. Okay? Here is 1, 2, 4, 6, 8, 1, 10 million. Okay? Alright? You see again is the markings. 1 million, 2 million, I think it's 4 million, 6 million, 8 million, and then okay? 1, 2, 4, 6, 8, 10. Alright? That's how it's plotted. Okay, so 2 million is about here. So that goes up to there. Okay, I zoom out a little bit. Oh, the brightness. Zoom out a bit. Okay. So 2 million is about here. And go up. Drag coefficient around 0.5 to 0.6. 0.6 or 0.7 like that. Let's take 0.6, okay? Alright? Depends how your skill of reading the graph. Okay? So, we take that back here. Okay. Computer 1. Okay. We take that back here. Our CD. our CD is F D over half rho V squared DL, which is equal to what is it? 0.6. Okay, from the graph, right? Because that graph done because other people have done the experiments earlier. Okay, and therefore FD is equal to 0.6 times half times rho is 1.23 times velocity is 10 squared, diameter is what? Diameter is 3, and the length, how long is our cylinder? No, diameter, so just put 1 meter. Alright, that is the length of our cylinder. Alright, 3 is the diameter, L1 is the length. Okay, I just made that up, huh? Okay, just for our case here, let's just work out the force for 1 meter of cylinder. Alright, force per unit length. Okay, alright, what is it? 0.7 newtons. Okay, so for 1 meter of our cylinder, this is the average force due to the wind. Okay, save. Okay, any questions? Copy down it. Right. So finally, okay, you use the video. Video. Come on. Alright. Now down please. Okay. So this is from your textbook. Alright. Hope you at least opened it once before. Okay. Slow down. So a lot of the standard items, alright, standard problems have been done before. They have compiled the data. It could appear in textbooks. It could appear in journal papers, research papers, and so on. Alright, where you can extract. So you don't have to. Alright, in every case we do the experiment because that one is expensive, difficult. Likely there are a lot of problems. Alright, so your textbook we have quite a number of simple ones. Okay, for example, the drag coefficient for all the basic shapes. Alright, as a function of Reynolds number. Okay. Okay. Alright. So from about 1,000 all the way to about 10 million. Okay. That's the drag coefficient if you have a plate, cylinder, and so on. Okay. We'll talk a bit more about this when we do the next chapter on external flow. But it's suffice to say, okay, you'll be using a lot of this. Sometimes they come in the form of graph. Sometimes they come in the form of an equation, like a curve fit equation. Alright? CD equals to something, 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 RE to the power something, something, or something like that. Alright? So don't panic. Either one can be used. Okay? Example. Alright? Okay. So, finally, this is another example. Alright? Up to now, you might think everything depends on RE. No, that's not the case. Sometimes the controlling parameter is not Reynolds number. Alright? Sometimes the controlling parameter, in this case, is the Froude number, FR. Alright? Because in this case, alright? Okay. For both moving on the surface, Alright? The biggest drag component is not from the flow per se, but it's from the waves. Alright? It's called wave drag. If you ever sit on a boat, you see there are two big waves that form on the front of the boat, correct or not? And they follow the boat line. Alright, it's the boat pushing the water out. Okay? It's those two big waves, and therefore, and that contributes a lot to the wave drag. Right? So boat, actually, if you move fast in the boat, it's actually very energy consuming. Okay, because of the very high drag. Okay? So that's why the big boats move very slowly. Okay, they move normally 10 knots to about 15 knots. 1 knot is slightly more than 1 mile per hour. Okay? 1 nautical mile per hour. Alright? So they move very slowly. If you want to move very fast, alright, like jet ski, all that, then your fuel consumption very high one. Anyone try that? Okay? So the jet ski or power boat or what, so you have to fill up with big tons of petrol, and then you go around for about half hour, all finish it. Okay? So because the drag, you need a lot of force to overcome the drag. Okay? So, in this case, because the controlling one is the waves, and the wave is, I told you the wave restoring force is the Froude number, so the wave controlling parameter is the Froude number. So in this case, there's Froude number here, okay, and the drag coefficient, for the wave drag anyway, which is the main component. So if your boat, conventional design, just a boat like that, the drag curve is like this, it's higher. More recently, a lot of the ships have a bulb here, bulbous bow. You seen before? Alright? Some have seen, some haven't. Okay, I'll show later. Alright? So this one actually helps to cut through the waves and reduce the drag by quite a lot. And save a lot of petrol or diesel. Alright? Mainly the big ships have it. Okay? Alright, what do you call it? Bow bulb. Okay? So for those who let's see. Okay, so I'll switch back. Okay, so this one I go back video. Okay, so example of it like this. Alright, so a lot of ships. Okay, this is the front of the ship. There's a little bulb here. This is another picture of it. Okay, and another picture of it. Okay, so lately most ships have it already. Most of the newer ships have it to save fuel. Okay, normally this bulb is under the water line or just barely. You sometimes can see, sometimes cannot, because it's just at the surface or just below the surface of the water line. Okay, so you really can't see it in the boat. Okay, but in the boat's out of water, you can see it. Okay. Sometimes dolphins like to follow here because they get a free ride. Okay, because the water is pushing them forward from the boat, so they get a free ride. Okay. Okay. All right. Any questions? All right. All right. One announcement. Thursday lecture. No, not cancel. We already need to make up some lectures. All right, along the way, so we can't be cancelling more. All right, so Thursday lecture, I'm not going to follow exactly the order of the lecture slides here. Okay, the lecture slide, I think next one goes to them external flow, boundary layers, all those type of things. Okay, Thursday lecture. Because we all now very familiar with dimensional analysis, all right, I'm going to move the dimensional analysis associated with the pumps to Thursday's lecture. So we do dimensional analysis for pumps. Okay, if you want to prepare, you can do that one. Because I realized if I do it later, you all have forgotten what we done earlier. So I myself do it now because this part, you don't really need to know how the pump works yet. It's just analyzing through the parameters only. Okay, so we do dimensional analysis on pumps on Thursday. followed by the remaining unit later. Okay?